class today with a little bit of an activity. Rather than lecture and then activity, we're going to reverse it. So we have a lot of experience with certain kinds of functions. We've learned a lot about linear, quadratic, polynomial. We've talked about piecewise functions. So this chapter, we're introducing two new functions, the exponential function and the logarithmic function. So today's class is all about the exponential function. So to introduce you to it, I'm going to have you in your groups work through this activity about rabbits. Okay, so we're going to let R of t be the number of rabbits on Rabbit Utopia after t years. So R of t. What's my formula going to be? Assuming that we start with 1,000 and the population increases by 1,000 per year. Yep, 1,000. That's how much we start with. And then we add 1,000 per year for t years. So 1,000 times t tells you how much to add total. What kind of function is this? 1,000 plus 1,000t. Linear. Good. So we should be really familiar with this kind of problem. Okay, solving a problem this style. It's just a linear growth problem. So now we move on and we say, well, the rabbit population that we were just looking at is probably not realistic, because as the population gets bigger, there are going to be more and more rabbits having babies, so the population is going to grow faster and faster, right? So it might be more reasonable to say that the rabbit population will double every year. You know, if every rabbit couple has 2 babies every year, the rabbit population is just going to double and double and double, right? It's keep getting bigger and bigger and bigger. So assuming that it doubles every year, we're going to fill in this table, and then we're going to rewrite our answers in the third column. Okay, so 1,000, you double, you get 2,000. When you double 2,000, you get 4,000. Double that, and you get 8,000. And double that, and you get 16,000, and then 32,000. So then I want to rewrite each of these numbers, 4,000, 8,000, 16,000, 32,000, in the format that I've given you in this third row here. So 1,000 I rewrote as 1,000 times 2 to the 0. And 2,000 I rewrote as 1,000 times 2 to the first. So 4,000, I could rewrite that as 1,000 times 2 squared, because that just says 1,000 times 4, which is 4,000. And 8,000 I could rewrite as 1,000 times 2 cubed, because 2 cubed is 8, so this says 1,000 times 8, gives me 8,000. 16,000 I could rewrite as 1,000 times 2 to the 4th, because 2 to the 4th is 16. And 32,000 could be 1,000 times 2 to the 5th. 2 to the 5th is 32. So using the third row as a pattern, what would the population be after t years? You got it. 1,000 times 2 to the t. Right? In year 1, it's 1,000 times 2 to the 1. And in year 2, the population is 1,000 times 2 to the 2. And in year 3, the population is 1,000 times 2 to the 3. So in year t, my population will be 1,000 times 2 to the t. So then I want to sketch this graph to look at its end behavior. So I'm going to have to use my graphing calculator. And I want to graph 1,000 times 2 to the t. 1,000 times 2 to the x, because x is my independent variable on the calculator, so I'll use x. And then I have to choose a good window. T is representing time, so it wouldn't really make sense to go before 0, except that they did ask me what happens as t goes to negative infinity. So maybe negative 10 to 10 would be fine. And then y is representing the number of rabbits. And at year 0, how many rabbits do I have? 1,000, yep. Can I ever have fewer than 0 rabbits? No. So I'll put 0 as y min. And then if I look back at this table, the number of rabbits grows very quickly from 1,000 to 32,000 in 5 years. So maybe I'll put 50,000 as my y max, a large number of rabbits. And press graph. And I get this picture here. Maybe I don't need to look so far back in time because I can't really see what's happening way over here. So I'm going to adjust it just a little bit. Maybe I'll go -2 to 7. Let's see how that changes things. That's a little better. Okay. So what happens to the graph? What happens to the number of rabbits as time goes to positive infinity? Let's see. So as t approaches infinity, the population of rabbits approaches what? Infinity. It gets really big, right? So as t goes out to the right, my graph goes up towards infinity. And then as t approaches negative infinity, what happens to the number of rabbits as I move to the left? It gets smaller, yep, but does it ever get negative? No. So it's going to approach 0. And another window might help us see this. So if I go, let's say, to -10, and I'm going to use a much smaller window for my y, just say 0 to 1. Actually, maybe I'll go 0 to 1,000. Now it's easier to see that as I go left on my graph, as t goes to negative infinity, the values of the number of rabbits is approaching the x-axis, or the t-axis, which is 0. All right, so there's my end behavior. Now I want to use the model to predict the rabbit population in 10, 20, and 50 years. So I'm looking for p of 10, p of 20, and p of 50. So I'm just going to have my calculator do it for me using the table. I already have the formula in y1, 1,000 times 2 to the x, where x is number of years. So I go to my table, and I'm just going to type in 10, 20, and 50. And I get really large values, right? 1.02 times 10 to the 6th. That means move the decimal places 6 places to the right. So 102,000,000. 1,020,000 rabbits. Another way to do this is to use the vars key. And if you're in the home screen, you hit vars, yvars function y1, and your calculator knows function notation. So you can put parentheses 20, right? And it'll calculate what you get when you plug 20 in. And then it gives me a more accurate answer than my table, because my table just can't hold that many decimal places, that many place values. So I get 104,857,6,000. 104,857,6,000. 1,048,576,000 rabbits after 20 years. It's pretty fast growth considering we started with 1,000 rabbits. Right now we have over 1 billion. Let's see what happens if I plug in 50. Now it's so big that even my graphing calculator can't write out all the decimals. I'll just say 1.13 times 10 to the 18th. which means I want to move that decimal point in 1.13 18 places to the right. It's a really large number. Now, does this seem sustainable, this kind of population growth? No, it can't continue this way indefinitely, because eventually what's going to happen? Rabbits die. Why would they die? Food supply, space, limited resources. There's only so much water and so much food and so much space, right? So in reality, they might start growing like this by doubling every year, because when there's only 1,000 of them, resources are plentiful and they just double away, right? So they might start at 1,000 and just double, 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 right? But then as resources start to become more scarce, the population's going to level out. So this might be a more realistic growth curve as opposed to the one we looked at in our calculator. This one that just keeps going up and up and up and up forever. Okay. This one might be more realistic. This is called logistic growth. Logistic. So it's not exponential, it's logistic. But today we're studying exponential. So let's sort of summarize what we learned here. In the linear model, what does this 1,000 represent, that first 1,000? Initial population. How about in the exponential model? What does the 1,000 represent? Initial population again. The 1,000 rabbits that we started with. So both of my 1,000s in my two formulas represent the initial population. The second 1,000 in the linear model, what does this 1,000 tell us? Growth rate. Yep, this is how we grow. Growth rate of 1,000 rabbits per year. Right? And then, well, that was B. What is the effect of the 2 in the exponential model? Why do we have a 2 there? Yes, because the population doubles. The 2 represents population doubling. Every year. So linear growth and exponential growth are pretty similar. They have similar components. They both have an initial value. They both give an initial value. And then they tell you how they grow. With linear, it tells you how many rabbits per year. And with exponential, it tells you what you multiply by. In this case, it would be 2 every year. We double every year. So they both give an initial population and then a rule for how to grow. So when we graphed the rabbit population, we saw a graph that looks something like this. How do you find a y-intercept in general? Set x to 0. So I'm going to do P of 0. That would be 1,000 times 2 to the 0, which is 1,000, because 2 to the 0 is just 1. So my y-intercept is 1,000, which is also my initial rabbit population, and it's a number in my formula. So that number represents 3 things, right? It's a number in my formula, it's the initial rabbit population, and it's the y-intercept. So horizontal asymptote. So an asymptote is a line that your graph approaches and gets really, really close to. Okay, so does my graph have a line that it approaches, that it gets really close to, but never crosses? Yeah, the x-axis. This line right here, the x-axis, my graph gets really close to. It just keeps coming down closer and closer and closer, but it never crosses it, right? So we call this an asymptote. This green line is called an asymptote. And the equation of this line, the horizontal line, so its equation is y equals 0. Because every point on this line has a y coordinate of 0. So the definition of an exponential function is a function that has a base a, and it's going to just be y equals a to the x. F of x equals a to the x. A has to be positive, and a can't be 1. So I want to talk about these restrictions on a. Why can't a be 1? We'll start with that. Anything to the first power is the number itself, right? But I'm not raising to the first power. A is the 1, not the x. Yeah, because if a was 1, my formula would be f of x is 1 to the x. And anything to the 1 to the anything is just 1, right? So f of x equals 1 has no growth at all. It just looks like this, right? Which is a line. This is not any new kind of growth, right? This is something we've already studied. So we say in order for this to be exponential growth, like the rabbit population, a can't be 1. If a is 1, it just looks like something old we've studied before. Okay. What if a were negative? What if I had something like f of x equals -2 to the x? If I had that base as a negative number, what would happen? Yeah, my even powers and odd powers would have opposite signs, right? If I make an XY chart here, and I did say 0, 1, 2, 3, 4. Well, -2 to the 0 would be 1, because anything to the 0 is 1. -2 to the first power would be -2. -2 squared would be -2 times -2, which is +4. -2 cubed would be -2 times -2 times -2, which would be -8. And -2 to the fourth power would be +16. So if I were to plot these, I would get -2, 2, 4, 3, -8, 4, 16. I'd get this like zigzagging thing where I go positive, negative, and the spaces are getting further and further apart. This isn't exponential growth. Exponential growth is just getting bigger and bigger and bigger, right? So in order to create what we think of as exponential growth, we have to make sure A is positive and not 1. Otherwise, we get some other kind of phenomenon happening. So keeping the base a positive number that's not 1, we really only get 2 flavors of exponential growth or exponential functions. We get growth and we get decay. Growth happens when the A value is bigger than 1. So you're taking your population, your initial population. In this case, we're doubling every year, multiplying by 2. When you multiply by a number bigger than 1, you get growth. In this case, I'm taking my initial population and multiplying it by 1/2 every year. Multiplying by a fraction that's smaller than 1, you get decay. You get a shrink. Okay, so my population would start at 1,000 and it halves every year, so it's going to go down. Okay, so we call that exponential decay. It happens when the base is less than 1. So let's look at some properties of exponential functions by looking at sort of an example of each flavor. We have a 3 to the x and a 1/3 to the x. And I'm going to study their properties. So the domain. If I look at the 3 to the x, the red function, this is strictly the red one. What is the domain of 3 to the x? What values of x are you allowed to plug in there? Slash, what values of x are covered by the graph? Yep, good. Negative infinity to infinity. All real numbers. You can raise 3 to any power you want. There's no restriction on what values you can raise 3 to. And the red graph here covers all x values from negative infinity to infinity. How about the blue graph? What's its domain? 1/3 to the x. Any restrictions? Nope. Same thing. Negative infinity to infinity. The blue graph also covers all x values from left to right. Going back to the red graph, y equals 3 to the x. What is its range? What y values get covered by that graph? 0 to infinity. Should I include the 0? No. There is no number x that I can raise 3 to it and get 0 as an answer. I can never get 0 as an output. So I'm not going to include the 0. How about with the blue graph? What's its range? Nope. Y values covered by the blue graph. Starts here, right? It goes up. So it's the same, 0 to infinity. The lowest y value you can get for this blue graph is 0. You can't even get 0. It approaches 0. And then you get bigger ones. Looking at just the red graph, is it 1 to 1? Does it pass the horizontal line test? Yes. How about the blue graph? Yes. So what? What does being 1 to 1 tell us about exponential functions? It has an inverse. Very good. So I know that exponential functions have an inverse. We'll think about what that is another day. Do either of these graphs have any extrema, local maximums or local minimums? The red one is always increasing, and the blue one is always decreasing. So there are no local extrema in either of them. And then finally, I just want to do end behavior. So for the red graph, as x approaches infinity, what happens to y in the red graph? As the x's get really large, the y's go to infinity. And as the x's get really small, as my x's head towards negative infinity to the left, what are my y values approaching? 0. Good. Then I'm going to do the same thing for the blue graph. As x approaches infinity, y approaches something, and as x approaches negative infinity, y approaches. So as x approaches infinity, what happens to the y values on my blue graph? Okay, so my x's are going to the right. My x's are going to the right towards positive infinity. Where are my y's going? Say it out loud. 0. Thank you. Y's are going to 0. And then as my x's approach negative infinity, as I move to the left, what's happening to the y values of my graph? Towards infinity. Thanks. So exponential functions, whether they're growth or decay, have a lot of the same properties. They have the same domain, same range, they're both one-to-one, no extrema, and their end behavior goes to infinity in one direction and 0 in the other. It just depends which one, if it's growth or decay. All right, so I want to find formulas for these two graphs. So this is sort of our ritual when we learn about new functions. We look at it in a sort of a real-world context, like the rabbits. We look at its graph and its properties, and then we have to learn how to find a formula for a graph. So this is just y equals a to the x. Right? Well, what's my initial value here? Let's I'm going to call this a not for a initial. Okay. So remember the rabbit population was 1,000 times 2 to the x. The 1,000 was the y-intercept, and the 2 was how you grow. Okay. So what's my y-intercept in this first graph? 1. And how do I grow? So this I have, if I made a little XY chart for these points here, one point I have is 0, 1, and the other one I have is 2, 25. How do you get from 1 to 25? What do you multiply 1 by to make a 25? Oh, right, 25, right. And I skipped an x value, right? 1, I don't know, 2, 25. What does that point look like? 1, what? 5. So what do you multiply 1 by to make 5? 5. What do you multiply 5 by to make 25? 5. So I'm multiplying by 5. over and over again. So 5 is my number that I multiply by. So I end up with 1 times 5 to the x. Sure, you can just look at it and figure that out without drawing a table. So let's look at the next one. What's my A0? What's my initial population or my y-intercept? In the second graph here, y-intercept is 3. Well, it's on your paper too, if you can't see it. It's 3. And then my next point here, so I have 0, 3. My next point is 1, 6. What do you multiply 3 by to get to 6? 2. So I'm doubling. My y values are doubling for every x value. So this should be times 2 to the x. So all you got to figure out is where you start. That's your first number. And then how you're growing. What are you multiplying by to grow? So is this exponential growth, this table I've drawn here? Yes, because it's doubling. That's great. If you're always multiplying by the same number to get from y value to y value, that's our definition of exponential growth. So a formula that would model this well, what would my y-intercept be, or my starting y value? 3. Yep. Your y-intercept happens when x is 0, so that would be 3. And then I'm doubling, so it's 3 times 2 to the x. You can always check when you found a formula by plugging in an x value and seeing if you get the right y. Right? So if I plug in a 4 here, 3 times 2 to the 4th, I'm hoping to come up with 48. 3 times 2 to the 4th. So if you just pull up your calculator, type it in. 3 times 2 to the 4th, and I get 48, just like my table says. So you can always, you always have a way to check if your formula is correct. We could have done that here too. Here's my formula, 1 times 5 to the x, and the point 2, 25 should be on there. So if I do 1 times 5 squared, yep, I get 25. Just plug in a 2 for x, I should get the appropriate y value. Okay, so the last thing is that now that we have a new kind of function in our family of parent functions, we can do transformations on it. So what transformation has occurred here? If this blue line is y equals 2 to the x, what transformation has happened? Reflection over the x-axis. Okay, so how do you adjust the formula to cause a reflection over the x-axis? Make the whole thing negative. Y equals negative 2 to the x. You just throw a negative on the outside of the function, because that will take all your y values and make them negative. All right, let's look at this second one. The blue is y equals 2 to the x. What does it look like happened? What transformation took place to turn it into that red function? A vertical compression. By how much? Factor of a half. Yeah, you can tell by looking at the first, looking at the y-intercept. It used to be 1, and now it's at a half. Okay, so I shrunk it by a factor of a half. How do I know that I did a vertical shrink as opposed to a shift down by a half? Because the asymptote is the same. Yep, it still goes down to 0. Okay, if I had shifted the whole thing down, my asymptote would have moved also. All right, so a vertical compression by a factor of half. A factor of a half. How do I change the formula to accommodate that? Multiply the whole thing by a half. So this is going to be y equals 1/2 times 2 to the x. All right, now looking at this last one, y equals 2 to the x is in blue. What transformation does it look like happened? Shifted up 1? Yep, it definitely looks like that if I check the y-intercept. It used to go through 0, 1, and now it goes through 0, 2. The asymptote moved up 1 from the x-axis to y equals 1. So it looks like a vertical shift by 1 unit, right? So how do you change the formula to indicate a vertical shift by 1 unit? Just throw a plus 1, yeah. So this would be 2 to the x plus 1. So we should be able to check any point. So 1, 2 used to be on my graph. Now it should be 1, 3, which is right there. So it does seem to fit our idea. All right, so that is it for the lecture. I have one thing that I would like you to do for me. This is a little survey about WebAssign. So I'm just looking for, well, the math department in general is looking for some feedback on how this is going. When you finish it, the remainder of class you can spend working on your project or whatever you need to work on.